Anyone got any questions before we get started? All right. In that case, we're going to start off with a quick sample review. We've been working with Newton's laws, describing how different forces work together and follow said laws. We're going to start the day off with a quick sample question that I'll throw your way. Give you a couple minutes to ponder it on your own, or among yourselves, plural. We have a 10-kilogram box that's going to be being pushed horizontally along a flat surface. The two forces that we know of that are currently acting on it are a 200 Newton force west, or left, or negative x, and a 250 Newton force east, or right, or positive x. And I'd like you guys to ponder these questions real quick, namely, draw a free body diagram showing all of the forces. What are all of the forces that would be acting on this box? What net force would they all add up to, and what would the resulting acceleration of this object be? Think about it for a second, and then we'll all compare notes and talk about how I think it all works. All right. How many forces did you draw on your free body diagram?
4.
4. We are told about 2 of them. The 200 this way and the 250 this way. If this thing is being pushed, bless you, along the ground, what other forces must be present, given what we discussed on Monday and Wednesday? Gravity and normal force. This takes place on Earth. You have to have gravity, and if it's on the ground, it's going to be pulled into the ground, and the ground will likewise push back. So, very good. There are 4 forces here. What do those 4 forces add up to if this thing is being pushed sideways? Very good. Within the x-axis, there's only 2 forces that oppose each other. So 250 plus 200 would give you 50 newtons to the right. Meanwhile, we just also consider the vertical axis. If this thing is being pushed sideways along the ground, is it accelerating up or down? No, and therefore, no matter how much this box weighs, the net force in the vertical axis must be 0 for it to be sliding only sideways. Now, with this in mind, what must the values of normal force and gravity be? Very good. And to find that, we would just use the formula that has been living over here, Fg equals m times g. So 10 times negative 9.8. Therefore, the box has a weight of 98 newtons downward. And if gravity is pulling with this much force downward, our analysis of the net force tells us that normal force must be pulling upwards, pushing upwards, with the same amount of force. Take note, on a test I may ask you to make a diagram like this and find numbers for every force present. Questions thus far? All right. Lastly, if the box's mass is 10 kilograms, what would its resulting acceleration be? Five. Very good. Net force equals ma. Therefore, 50 to the right is going to equal 10 times A, and A will be 5 meters per second squared, also to the right. Because according to Newton's second law, the direction of the net force matches the direction of the acceleration. They inherit their directions from the other. Similarly, if something is accelerating down, that means the net force from gravity points down. How you guys feel? That's some quick application of what we did on Wednesday. All right. So, we're going to close out this week by looking at a few more types of force, namely, well, there's 2 on this slide. I'm really only going to talk about tension today, and we'll do friction next week. Just because tension, I've got an example planned that will take up most of the rest of the lesson. Don't worry, it'll be fine. So we're going to define tension for now. We'll come back to friction. So more types of force, looking at where it comes from, how it interacts with other forces, and how they interact back with Newton's laws of motion. Tension is one of those types of forces that people have heard of and frankly use pretty often, but I want to make sure that you guys have the physics definition for it. And if I was to try to summarize tension to a short sentence, it would be the force that ropes will exert. Ropes exert tension. Now, the more drawn out definition is that tension is the force that an object exerts as a, sorry, I'm going to end myself. Objects exert tension when they are being pulled outward on both sides. And likewise, tension is therefore the response, the reaction force to those forces pulling outwards on either end, causing the object in question to pull inward on both ends. You probably heard the phrase under tension, which frankly applies to most people these days. I'm going to demonstrate using this spring. While I'm holding it like this, is it currently under any tension? Not really. In order to be under tension with the physics definition of the term, something has to be pulling outwards on both sides. If I'm just holding it like this in my hand, the forces present aren't acting directly in that manner. Gravity down, normal force up. I'm not pulling directly on either end. So right now, this is not exerting any tension. This spring only exerts tension as a response when I am pulling outward on either end. So right now, the forces I'm exerting point out on both sides. Both of my hands are pulling outward on either end. From your perspective, this hand is pulling towards the right on this side of it, and my other hand is pulling to the left on the other side of it. And as a response, the spring is going to pull on both of my hands inward on either end. And that means it's actually pulling in two different directions simultaneously. So I'm going to draw out what I'm demonstrating with that. Any issues if I erase our previous work? So, this black box will be a stand-in for a rope. It is just a very poorly drawn rope. And I'm going to draw two orange arrows representing the forces that I am using outward on either end of the object. I'm just going to make them 10 newtons as a sample number. And so that is what I am doing. Both of my hands are exerting two different 10 Newton forces outward on either end. That is not what the rope is doing yet. As a response to that, because Newton's third law says that every action force causes an equal and opposite reaction force. So on this side of the rope, if I am pulling leftward on the rope itself, Newton's third law tells us that the rope's response is going to be to pull rightward with 10 newtons as a reaction back on my hand. And that's why when you pull outward on something, you feel it pull inward in the opposite direction. It's exerting a reaction force on you. So on this side, it's going to pull this hand rightward. But what's curious is that the same but inverted thing happens on the other side. Because on the other side, my other hand is pulling rightward. And so as a response, the other end of the rope is going to pull that hand leftward. So the green again represents what the rope is doing. The green are the forces the rope exerts. And so as a response to me pulling outwards on both ends, technically in two different directions, the rope responds by pulling inwards on both ends, again, technically in two different directions. The weird quirk of ropes is they can pull in two different directions at once on either side, but it's always the same number on either side. Just going to add real quick. Sometimes tension is just capital T. I would prefer, if I was writing the textbook, to call it F sub T, but enough formula sheets and textbooks use just capital T, but I want to make it clear that that is an option for it. That said, T is one of those letters we use a lot in this class. There's a completely different concept that instead of capital T, uses capital Greek tau. So that'll be fun later. But, as I said, we'll deal with that headache later. Tension is weird because it can pull in two different directions simultaneously, which is weird to describe out loud if you've never thought of it that way, but you've definitely noticed it happening. Whenever you've played tug of war, as an example, you would pull in one direction on the rope, and as a response, you would feel it pull in the opposite. Because I'm going to switch sides actually. If this is me playing tug of war and I am pulling leftwards on the rope, you can feel it pulling rightwards back, trying to rip out of your hands, correct? But then on the other side, the other team is pulling in the opposite direction. You can see the rope pulling inward on them, because if I yank really hard on this side, the other team is likewise going to get pulled towards me, because if I'm pulling harder on this end, I'm increasing the tension that the rope is under, and it's going to in turn pull harder on the other team. That said, it's important to note, these two will always be the same. The rope always exerts the same tension inward on both sides. It has to. Even if the two forces on either end are imbalanced. So to change the picture slightly, this is a thing that can happen. This would be basically a game where this team is winning tug of war and this team is losing. Notice the rope is doing the same thing on both sides, but the two different teams are outwardly using different levels of force. And that's why on this side, net force points left and this team successfully walks backwards. And on this side, net force still points left and this team gets dragged forwards. But the tension is still the same on both sides, even if the force outside the rope is imbalanced. So this is a thing that can happen, but the two green numbers will always be the same. This is what lab next week will be about. Another case where this comes up sometimes, depending on your movie tastes, is if the rope is instead oriented vertically and some action hero is trying to swing from it. We kind of pause time right here at the bottom of the swing. This person's weight would be the separate outward, downward pointing force, and the rope responds by pulling up on this person. Meanwhile, on the opposite side, because the rope has to pull inward two different directions, the rope is going to pull down where it connects to the ceiling. And that's where you sometimes get that tense moment where the rope is like pulling the rock loose if the rock cannot handle this much force. So however much force the rope is pulling up on you, the ceiling where it connects has to be able to handle that much force, which is why I have not just poked a hole in these ceiling tiles and tried to swing from them, because these things were not built for me to be able to George of the Jungle around the room. The ceiling tiles would collapse, and I would have a very upset tailbone. You believe in me? Tangentially related, first of all, thank you. That said, I've never been very good at supporting my own body weight with my arms. Separately though, there are support beams in the ceiling behind the ceiling tiles, and I know this because when I was a student at PC, one of my hall mates had a room to himself. And he just either wasn't assigned a roommate or no one showed up. So he had the room to himself, which means he had extra space to pull out the ceiling tiles and hang a hammock from the support beams. So you can hang things from the metal parts, just not the cardboard parts.
Are we allowed to do that?
I wouldn't recommend it, because if your RA comes in and looks up and sees the ceiling, like sees inside the building, that might be a problem. It was really a problem for the hallmate in question, because rather than remove the ceiling tiles, he literally cut holes in them. So definitely don't do that. I think he had to find spare ones before he moved out. Questions about tension thus far? All right. Again, the weird quirk is it can pull in two different directions at once. And that can make the math kind of funny. So we're going to practice that math. Here we have another scenario involving ropes. And the math we're about to do is the type of thing you would do if you were, say, some sort of engineer, either doing statics or mechanics or set design, possibly. Here we have a series of ropes holding aloft a pretty heavy box. It's about the same mass as me. And again, practically what you'd want this system to do is to be able to safely hold all of the tensions required to keep everything in place. So what we're about to do is figure out what the tension in all of these ropes is. And again, what an engineer would do is they calculate all these tensions ahead of time. They figure out how much tension each rope would bear in this situation, so that they could then pick the right type of rope that can hold that weight without snapping. So again, the math we're about to do is to predict tension. You would need to know that tension before you build it so that you don't use the wrong type of string or rope or cable, etc. And we are going to figure out the tension in all of these ropes. There's 3 ropes, meaning that there's 3 separate tension values, and each rope is going to exert that tension in 2 different directions at once. So I have taken the liberty of drawing 6 arrows in advance, because each rope pulls inward on both ends, making it slightly different for each one. There's 3 ropes here, so we're after 3 tensions. I have labeled them 1, 2, and 3 in reference to the angle numbers as well. So 1, 2, and 3 scaling counterclockwise around. I'm going to describe the 3rd one first. This is the rope that is most directly connected to the actual payload. It is going to have to pull up where it connects to the box, and that means likewise it's going to pull down where it ties into the other ropes. Said ropes, since they are being pulled down upon here, they have to exert vertical force upwards to counteract that. So T2 is going to pull up and leftward along its own length. Meanwhile, where it connects to the ceiling, it will, like as an opposite, pull down and rightward. T1 has to pull up and rightward at this knot. Likewise, it will pull down and leftward where it connects to the ceiling. So 3 numbers, but 6 different directions depending on which spot you're looking at. And we got to figure out what those numbers are. Questions about the premise before I start doing some math? All right. If our goal is to find all the tensions, we need to see how they all interact with each other. And there are 2 key locations where tensions are acting in this picture that I think will be useful to us. Because in this broader scenario, there's several key intercepts where various things are interacting. These 2 top ropes connect to the ceiling, T3 connects to the box, and then there's this point in the middle where all 3 of them interact. When examining compounding tensions like this, in a question like this where you are seeing how the tensions all work together, my first step is to pick a few of those points and try to describe the net force of that location, and likewise what forces are all adding up into that net force. To try to demonstrate this, I'm first going to draw your attention to this particular knot right here. At this spot, all 3 tensions are acting simultaneously. They are all pulling on this particular node. And so, since they're all acting at that spot, they're all going to be contributing to the net force at that location. So for this particular spot, I'm going to write out net force is equal to, and they are all here acting, all here contributing to that net force value. So they are all adding up to and contributing to net force at that location. Now, my main question for right now, if the goal of this entire assembly is to hold everything in place, both the box and all of the ropes holding it there. If you want everything to remain stationary, what does that tell you about your desired net force in this system?
Equals 0?
0, exactly. If you want something to remain stationary, you need all the forces acting on it to add up to 0. This is what architects and industrial and civic engineers spend all day doing, making sure all the forces on every part of their structure add up to 0 and that nothing breaks. So there's several disciplines dedicated entirely to doing this. It's very important. So, want to stay in place, net force has to equal 0. We have 3 things here adding up to 0, and since we don't know any of them yet, this line of inquiry has kind of reached its logical endpoint for now. We'll come back to this later when we have more information. I'd now like to draw your attention to a different spot that might provide us some information. We're going to look at all the forces that are adding up to net force here, where rope number 3 ties onto the box. So, separate frame of reference, a separate knot over here. Don't drop your markers. At that spot, what forces are going to contribute to the net force acting right there where the rope connects to the box? Weight of the box. So I'll just write that here as force of gravity box. Is that the only force acting at that spot?
Maybe T3?
Yep. The rope is tied physically to the box. So at this location, T3 is acting and pulling up on the box as the box's weight tries to pull it down. So those 2 forces are interacting here at this location. And what must those 2 forces add up to if our main thesis here is keep everything in place? Still 0. You want every net force all over this entire assembly to be 0. And that can give us more information, because there's only 2 things in it, and we have enough information to figure one of them out ahead of time. Because if we know the box's mass, what can we find? Yep, the weight of the box. Yep, negative 980. So weight of box is going to be mass of box times G plus T3 equals 0. So that's 100 times negative 9.8 plus T3 equals 0. Negative 980 plus T3 equals 0. Therefore, at that spot, T3 must be positive 980 newtons. That must be true because at that spot, that one rope is holding the entire box vertically. It's important to note, all this work we just did is very specifically y-axis work. There's no x forces present at that location to speak of. How do you guys feel arriving at this conclusion? All right. So that's one of the 3 ropes completely done. We know the tension in the 3rd rope. It points up here, and likewise that same number is going to be pointing down here. And then we can now take that number and use it in our further summary of what's happening to the other knot at the point where all 3 tensions converge. So we now have a number for T3, but there's a small issue with that number. It's y-axis only. T3 is the only rope here that is pointing in a single axis. The other 2 ropes, we don't know what T1 and T2 are yet, but we know they're at weird angles. This one's at 30 and this one's at 45. And that means whatever those numbers are for those hypotenuses, they are not entirely within a single axis. They have components. And that means that this initial equation written here, even if we had numbers for all three of them, they wouldn't actually add up to 0 if used this way because they're not all in a single axis. So before we do much other work, we have to actually take this and turn it into two separate equations, once for each axis. Does that sound okay so far? Okay. So first up, I'm going to write out the x version. So just looking at the x forces present at this position, that'd be T1x plus T2x plus T3x equals 0. That said, what is the x leg of T3? It's 0, so this whole piece is just going to go away. I'm writing it in for completeness sake, but T3x is 0, so take comfort in that. And then in the y, T1y plus T2y plus T3y is also, they also must add up to 0. And we have a number for T3y, it's that 980 we found earlier, because that's entirely within the y-axis. So I'm writing them with the components in for completeness sake, but we do have numbers. T3x would be 0, T3y is actually going to be negative 980, because it may pull up on the box, but it's pulling down here. That's why it's important to set your frame of reference anytime you start doing math. So we have to manually adjust our frame of reference to T3 pointing down at this position. So plugging in those two known values for T3, this is now where we're at. In the x-axis, we have the two x legs of the two triangles adding up to 0. And the y-axis, we have their y legs working together to cancel out T3. And the problem that starts to form here is we don't know any of these things. We don't have T1 or T2 or their legs. So now we have two equations with 4 unknown things in them. And that doesn't quite work. So before we proceed, we need to re-describe each of these legs in terms of the information we want. Because the end goal is T1 and T2, right? Those are the numbers we care about. And so my recommendation then for next steps is using trig to rewrite those unknowns in terms of the two hypotenuses that we don't know but that we want. Because again, we don't know the components, we don't know the hypotenuses, but we do know their angles. So we can at least make some informed assumptions about the trig. The way that I drew this, I labeled this angle as the 30, but due to complementary angles, the way I drew it, this angle would also be 30. And likewise, this would have been 45. Does anyone have any issues with how that works? All right. So what I recommend we do is look at these triangles, look at how these vectors break down into their components. We can't get numbers for the legs, but we can at least redefine the legs in terms of the unknown hypotenuses. Hypoteni, hippopotamus, hypothalamus. I'm gonna stop now. From this 30 degrees perspective, which of T1's two legs is the opposite one?
T1Y.
Yep, T1Y is opposite because it's the leg that isn't touching this angle, and that's going to leave T1X as adjacent. So, SOHCAHTOA, SOH, sine, opposite hypotenuse. Sine of 30 is going to be T1, I almost wrote X, T1Y over T1, which tells us that whatever TIY is, it's equal to whatever T1 is times sine of 30. We don't have either of these, but sine of 30 is a number. You can find a number for that. I'm just not writing it out because it's going to be a weird decimal that I don't want to have to remember. And SOHCAHTOA, tangent's not going to help us much here because it doesn't have hypotenuse in it, so I'm also going to use cosine of 30. CAH is adjacent over hypotenuse. So T1X is going to be our unknown T1 times the cosine of 30. And doing this takes our two unknowns and makes them in terms of the same one unknown, the one that we want. So we can then take those and plug them into these statements and eventually help reduce the number of unknown things, help make one of them in terms of the other. But we need to do the same thing with the y-axis first. Sorry, not y-axis. Same thing to the other vector triangle first, sorry. This triangle is oriented opposite it. Its orientation is a mirror image, so the same basic orientation will get you the same legs. It's not going to be a weird one where cosine gives you y instead of x, but do always make note of the orientation of the triangle as it's drawn. From this one's perspective, we would very similarly end up at T2y is T2 sine of 45, and likewise T2x will be T2 times the cosine of 45. It'll be the same equations, just using 45 instead of 30 and T2s instead of T1s. Just because the triangle is at least oriented in terms of the same angle structure. So the same trig functions would give you the same axis. I wrote a y instead of an x. How's that feel? All right. So now we have four separate things that we can plug into our two axes equations here to try to reduce the number of things we don't yet know. Looking at the x-axis, we would have, instead of T1x, writing T1 cosine 30, and instead of T2x, we've got T2 times the cosine of 45, plus 0 equals 0, so I'm just going to note equals 0. One other thing to note here before moving on, and your calculator probably wouldn't be able to tell you this, note that these x legs oppose one another. So one of them is going to have to be negative. If you don't do that, the math kind of stops working. Again, calculator doesn't have that frame of reference. We have to add it ourselves. And it does make the next step a little bit easier, because then we can just add the negative one over to the other side and get the two sides equaling each other. Reducing the number of unknowns, but we still have two of them, unfortunately. So this one equation, while simpler, still can't give us an answer by itself. But we can do the same thing to the y-axis as well. Instead of TIY, writing in TI sine 30. Instead of T2y, that's plus T2 sine of 45. these both point up. The vertical legs are working together against T3. So these can both stay positive. I'm going to go ahead and drag this negative over to the other side and just say equals 980. Bless you. And once again, we've reduced the number of unknowns, but this one equation still has two of them, unfortunately. However, do you see what we're working towards? This is one of those two equations, two unknowns tricks. We've gone from two equations, four unknowns to 2 and 2, and so there's still more algebra ahead, but it is now solvable. Two equations, two unknowns could also be known by the tagline, not fun, but possible, rather than not fun and impossible. So they're both now in terms of the same two unknown things, T1 and T2, so we can rearrange one into something we can plug into the other. The x-axis one is a little simpler, so I'm going to recommend rearranging this to be either T1 or T2 equals, because then that's fewer things to have to plug into the second one. So I'm just going to take this, bring it up here. T1 cos 30 equals T2 cos 45. I'm going to take that and I'm going to turn it into T1 equals T2 cosine 45 over cosine 30. You see how that works? And that gives us a bright, shiny new thing that we can write in place of T1 anywhere, including in the y-axis. So, looking at the y again, T1 sine of 30 plus T2 sine of 45 equals 980. Instead of that T1, we're going to write that instead. T2 cos 45 over cos 30 in place of that T1. And now, again, ugly looking, but there's only one unknown left. And is now technically in a solvable state. Any questions or issues arriving at that point? All right. T2 is now in two different spots, but conveniently, there's a single T2 being multiplied into both terms on the left side, so we can just distribute it out, which would look like T2 open parentheses. This is going to leave behind one weird-looking trig fraction, but it's just one fraction that does simplify down to a single number, thankfully. So, leaving behind all these bits that aren't the T2, and then handwriting is deteriorating. This piece would just leave behind the sine 45. And that's still equal to 980. Any issues with that distribution, or reverse distribution, I guess? Now this whole big thing in the parentheses, you know every angle in it, so you can just put this into your calculator to get one single number. Just be careful to put all the parentheses and order of operations stuff in the right positions. If you do it right, you should get 1.115. And that has now compressed all of it down into a single, fairly easy to remember number. And that's still equal to 980. So, last but not least, T2 is 980 over 1.115. which is 800 something. About 879. And that is the tension in rope number 2. A little bit smaller than the first one. If that trend continues, then T3 would be the biggest tension here. Any questions or issues arriving at that number? Okay. Now, all that 2 equations, 2 unknown work has boiled down into the simplest part, where you just take this new number and pop it into the other equation to get a number for T1. So this is the satisfying part. Take that, drag it back up here. T1 would now be 878.9 times a weird trig fraction. And if memory serves, that should also simplify down to a single number that is 717.6. So the forces actually get smaller as we proceed through the ropes. And that's every tension. How you guys feel? Now we're about done for the day, so as we wind down, I will point out that this is a lot of algebra. Test 1 is coming up in about 2-3 weeks now, first week of October. And I'll point out that if I gave you this as a test question, this would be the long